Everyone, welcome to the number 8 of the Low Latitude Atmospheric Research Working Group online seminar series. Today's speaker is Professor Yajun from the National Space Science Center in China, in Beijing, China. Professor Zhu, he did his bachelor degree study in physics from Yunnan Normal University. And after finishing his undergrad study, he went to Beijing to obtain his master's degree in space physics at the National Space Science Center, Chinese Academy of Sciences, in 2013. And then he went to Germany to work on his PhD degree in physics from the University of Wuppertal. And his specialty there is the photochemistry. And after his PhD, he went on to Jülich Research Center in Germany for 3 years as a postdoc before returning to the National Space Science Center. And he's now the professor there. And his research interest is in the satellite and ground-based measurements of the air growth using different techniques, spectrometer, as he will explain later on. And he has many very interesting publications. And I'm sure that he will be happy to provide you more information in his talk. And Professor Zhu, please start your talk. Thank you so much.
Okay, thank you very much for introduction by Professor. Yeah, I will share my screen. Oh, it's okay now?
Yes.
Okay, great. Good afternoon, everyone. I will give a brief introduction of the development of an asymmetric spatial heterodyne spectrometer for thermospheric wind measurements. My name is Yajun Zhu. I come from the National Space Science Center, Chinese Academy of Sciences. Okay, this instrument is a new type of interferometer for measure the thermospheric winds. And my talk includes 5 parts. First is the introduction. As we all know, there are many emissions in the middle and upper atmosphere. Here is, as I said, the red line, atomic oxygen green line, and the sodium emissions and hydroxyl and also oxygen emissions. Here we can see the different atmosphere will emit different type of rays with different colors. Another fantastic phenomenon in the polar region is aurora. It's a very high dynamic phenomenon in the polar region. These emissions peaking at different altitudes, such as atomic oxygen red line, peaked around 250 kilometers. The green line, it's around 96 kilometers, and hydroxyl is around 87 kilometers. Therefore, these emissions are good treasures for us. I mean, to detect, to observe, and to monitor the dynamic processes or photochemistry processes happening in the middle and upper atmosphere. As we all know, when atmosphere moves, its emissions will be Doppler shift. I mean, there will be a Doppler shift in the emissions. If we measure this Doppler shift, we use this equation to derive the speed of the atmosphere. The wind speed it's around and below. Typically, it's below 300 meters per second. However, the speed of light is 3 multiplied 10 to the power 8 meter per second. This means the Doppler shift is less than 10 to power minus 5 nanometers. Sorry, there are no instrument that can measure this Doppler shift directly. This means we cannot, to derive winds from the spectral frequency domain. However, if we, in the physics, if we cannot analyze the phenomena in this domain, maybe we change it to another domain, like the spatial domain, the interferogram. We will find that the interferogram is very sensitive to the wind speed. A very slight, a small wind will result a large interferogram shift. Normally, there are two typical interferometers used to measure atmospheric winds. One is a Fabry-Perot interferometer. Another one is a magazine interferometer. The LPI is like this. Here is ethylene, and it's a magazine interferometer. Nowadays, there's another technique named Spatial Heterodyne Spectrometer, named SHS. This instrument is similar to the magazine interferometer. The only difference is that two gratings replace the mirrors here. This setup will generate fatal fringes as the output. If we want to measure wind, this means we need a large OPD to observe a large MED. Maybe the larger OPD will generate interferogram very sensitive to the wind. So we enlarge, we prolong one arm to sorry, to make a symmetric setup. This means a symmetric SHS named DASH. DASH is a variant of spatial heterodyne spectroscopy with an additional optical path offset on one arm. DASH has its advantages, such as a low fabrication tolerance. The Fabry-Perot need divided by 100. It's very high tolerance, fabrication tolerance. It's difficult, to produce. There's no moving parts. For magazine interferometer, it has a mirror, to move. It can be made monologic and robotinist like this. Here is an example of the HHS. The size is 27 millimeters, and the height is 38 millimeters. It's very small, and it's also its highest throughput, like the magazine interferometer, and the small size. Now there are two, DASH have been developed by the Naval Research Laboratory. One is ready for ground-based atmospheric wind measurements. Another is mighty on the mission of NASA named ICON. That's optical path of the interferometer. Therefore, second part is we also want to design a DASH to make a atmospheric wind measurement. This is our observation scheme. We use the interferometer to observe the emissions. First, we should determine the emission lines. It's 613 nanometers. The spectral range is 613 nanometers. The resolution is less than 0.01 nanometers. And the throughput is larger than around 0.08 centimeter square per centimeter square star reading. it's typical LPI you can do to catch enough, throughput the signal. And the bandpass filter is around 1.5 nanometers. So we use retracing software to design a dash, the interferometer. Here the full field of view is 9 degrees, and its optical path difference is 32.6 millimeter at the center. And here the active grating area is 32 multiplied 32 millimeters square. The revolving power is very high, 15,600. And the you do is 0.2 around, centimeter square as the reading. But in reality is 0.01, because follows the rules of the magnetic parameter. Half of the energy will be reflected back. So we designed the interferometer, then we make a setup of the instrument to test the how to say the quality of the interferometer. Here we use a laser, to focus onto the integrated sphere to make a homogeneous emissions, and a buffer to limit the field of view. And here is the key components, the interferometer, and here's a telescope to image the interferogram onto the CCD detector. That's the interferogram produced, generated by the interferometer. Then we analyzed its fringe visibility, which is a very, very important, parameter to assess the interferometer. It's at the center, its visibility is 0.7, and at the edge, it's around 19%. I would say it's a quite good, design. And also because the interferometer is very sensitive to the temperature. 1 degree will introduce will result in a large phase shift. So we also designed a somewhat isolation setup to warm up the interferometer to 35 degrees. Temperature maintained 35 degrees, and after tests for half years, and we find that the accuracy is around 3 per 1,000 Kelvin. It's very stable. And we also measure the the space frequency and the phase offset, depending on the temperature changes. Find the green line is modeled, and the red line is a real data measured. We find that there are some differences. There are maybe two reasons. One is that when we glued the dash, maybe there are some gluing or the defects inside when we're gluing it, the tilt or some directions, and made the spatial frequency changes. And another point is maybe result from the material, because the material maybe is not the ideal condition, not in the ideal condition as we modeled. We write in the model. However, it's quite, rule there are some differences. It's quite how to say, the phase shift is quite good. Here we compare the two parameters. One is our design parameters is 0.5 reading per Kelvin, and the ground-based interferometer designed by Navy Research Laboratories, their value is 1.25 reading per Kelvin. Here we meant 1 milli reading will result in 1 meters per second bias. Therefore, why we need a very high, how to say, the temperature stability of the temperature. Then I will introduce how to, to modeling and correction in the interferograms. As we all know, when we gluing the dash, we cannot, keep the grating to two gratings parallel each other. There are still some, tilt in this direction, like beta 1, or also in another direction, in beta 2. So this will result in a tilt and defect in the interferogram. It often happens, when we gluing or bonding the dash interferometer. And some other tolerances, such as from manufacturing and assembly, imperfections of the optics, and imaging aberrations will inevitably distort the recorded interferograms. In this situation, we cannot derive winds from this interferometer, from this interferogram. We need to do phase distortion corrections to derive the useful information. Therefore, we modeled this in gratings, and we use a matrix, transformation matrix, to image, the fringe pattern without, defect to a real with defect equations. And use this equation, we can derive a phase correction matrix, phase distortion correction matrix. Here is one example of the phase correction matrix plot in X direction and in Y direction. Here is a CCD detector. We can see the phase changes, distortions changes with different pixels in X direction and in Y direction. Also, we set up a new optical setup to verify this. We use real data. One emission is around 630 nanometers. Another is 630.6 nanometers. We can see the tilt interferogram can be corrected after applying the phase distortion phase correction. Use the matrix. It can be, directly derive. We can derive winds just use the interferogram from this how to say, the corrected interferogram. This work is just published last year. And also instrument calibration is it's an important work when we put instruments in the field station. Therefore, we also developed a calibration system. To produce a Doppler shift, determine the Doppler shift. Here is a setup of the wind calibration system. The laser pass through the isolator, then use the laser to focus on the acoustic optical frequency shifter. Then use another lens to focus on the diffuser. Then to make to parallel or use another lens R3 to image to the interferometer. Before, I mean, in tradition setup is here's a rotating disk. It's the rotating disk will run very fast to make a Doppler shift. It's very dangerous. So we want to use we choose acoustic optical frequency shifter to replace the rotating disk to produce Doppler shift signals. Here we use light beat method to detect the phase. I mean the Doppler shift. Here's example is 100 megahertz. It actually can be derived use the light beat method. Here's a wind simulation. I mean use this setup to simulate I mean the wind. Here's the speed. This in y direction is shift frequency. We can see it's a very it's very accuracy, precision to simulate the wind. we just published this work in this year. Then we want to test this setup to demonstrate if it's good or not. Then we use a calibrate Fabry period interferometer first to derive winds. And I mean, in addition to the setup, we add another setup. It's a new lamp. I mean, to pass band pass because when we're measuring the interferometer, there are always some. I mean, the temperature will change, the pressure will changes. So we need a how to say a lamp or a calibrated source to trace the thermal shift introduced or result from the temperature change. Only a small difference. We can see here the measured speeds and the shift frequencies. We can see the MS is of the frequency is 1.5 megahertz. This means the velocity. I mean the velocity of the derived from the Fabry period interferometer is the uncertainty is around 1 meters per second. It's quite small. Then we test this use test prototype. I mean test the setup. We also I mean to calibrate this prototype, and we find the MS is around 0.4 meters per second with a light source. I mean the light source also has some uncertainties. The whole uncertainty is 0.9, around 1 meter per second. So this demonstrates that we developed various, I mean, the dash interferometer successfully, and also we calibrate this instrument. Next step is to, I mean, to make a field measurement and make a comparison with Fabry period interferometer. Here come to the conclusions. As a new dash interferometer is designed to measure thermospheric wind, and another is the performance of the dash are quite good. I mean, according to the laboratory tests and the demonstration, and also, I mean, we need a comparison. I mean, cross comparison with Fabry period interferometer in a field station to demonstrate that it's can be used in the in future. Okay, that's all my talk. Thank you very much.
Yeah, thank you so much, Professor Zhu. So you mentioned mainly the design or testing of this instrument called DASH. Maybe ask some of the experts here in the audience. Do they have questions? Any questions? Please raise your hands or just ask. Turn on your mic. And you're very welcome to speak to Professor Zhu. I recognize some names. John, are you there? Do you have any questions?
Hello, yes, I'm there. I don't have questions. Thank you. Thanks for the talk.
Right. But I mean, Professor Zhu, John is from South Africa, so I don't know whether you met him or not, but I think hopefully you could cooperate. Yeah.
I think the question that I would ask is really not scientific. I wanted to ask the presenter about the cost of the instrument once everything is assembled. What's the typical cost?
Yeah, I have the same question too, but I dare not ask. John, thanks for asking.
Thanks.
So how much is it? How much, how much is the instrument?
How much? You mean the price or?
Yeah. And how many people you're involved in doing this? I think that you spend a lot of time, right?
Yes, it's from 2016. I stayed in ULIS Research Center. We decided to develop this instrument, and then we around 3 people working on this project, and then we after I came to China in 2019, and we want to use this instrument to construct, I mean, to deploy it in some stations all over China. So I would say it's not so expensive. It's cheaper than than a Fab-Parodic interferometer.
So how expensive is that?
You mean the
in actual money wise? Yes.
RMB is 1.5 million maybe.
1.5 million RMB.
Yeah.
1.5 million. So John, you divide 1.5 by 4. That would be US dollars. Yeah, American dollars.
Okay. All right. Thank you. Thanks for that.
If you develop by yourself, it's quite cheap. But if you, to ask a company to produce the components, I'm not assembly by yourself. Yeah, because these components are assembly by ourselves, so we cannot calculate the price of that.
Okay, thank you.
Yeah, if you ask a company to produce this, it's quite expensive, I would say, because they should develop lots of setups to demonstrate it works.
Of course, by building things by yourself, you also establish, you develop your own skill.
Yes.
And that's more or less priceless. Yeah. So you earn from doing that. And do you have confidence this instrument will work?
We have done some experiments because at the moment in China the industry develops very fast. There are lots of contamination from the city lights or even in the countryside.
Mm-hmm. Where would you test your instrument? You say you want to calibrate and have some
in Huairou and also in Hainan province. We have a national station in Hainan province. And we get some results, and we do a demonstration with Fab-Parodic interferometer. We are still working on this project to make a comparison between them.
But it's very far away from having such an instrument on the satellite, right?
Yes.
I mean, you saw the slide about the icon. The mighty instrument is really beautiful.
Yes, the icon. Yeah, the icon is quite a success mission to measure winds.
Yeah. You also mentioned that in your thermal test, you are talking about accuracy of less than 0.003 degree.
Yes, the temperature, the stability of temperature.
And on the ground, you want to control that, right? On I mean, how do you measure? How can you control the accuracy to 0.003 degree?
We use PID technique.
Okay, and I see Andres. Andres, are you there? Andres Calabria, he is now in Spain, in Madrid. And,
Okay.
yeah, he used to work in Nanjing. And
Oh, great.
Yes, hello. Thanks.
Andres, you have questions?
You know, a little bit outside of my field. I mean, if we could compare with the thermospheric density or wind from accelerometer, so GPS could be very interesting. Yes.
Right. Any other questions? I can see names. I mean, there's a Ambu Ding Dang. Is that from Malaysia, right? Your question?
Yeah, thank you. Actually, I don't have any question. I thank the presenter for the nice presentation. Thank you.
Thank you. And Dennis? Dennis, you have questions? And there one person from NCU.
Yes, I'm here. Thank you
Dennis,
very much
you have
for the nice
questions? Yeah, please.
presentation.
Yeah. So I think most of us here just to try to get something out of this very complicated instrumentation. Yeah.
Yeah. Sorry, I prepared. It's very, how to say, it's not so many details there. It's
No, it's okay. Because as far as the instrument is concerned, you know, it's very nice that you now can build such an instrument, and that's a very important step, right? Okay. If there's no other questions, I hope that so when you're going to test the instrument and to get some real data.
It's the instrument is now it's under calibration with another instrument, parrot. I think we will have some results soon.
So maybe several months or a year later, you come back and we could listen to your results, real results.
Yeah.
Right?
Okay.
Yeah, that would be great. That would be fantastic. Okay, thank you so much, everybody. I mean that we have this is a quick presentation, but I think it's very nice and that's the way to go. And I want to thank Professor Zhu again and for this preparation. Yeah, and thank you everybody. That I hope that you come back again next time. Okay, thank you, everybody.
Yeah, you're welcome.
Yeah, bye-bye.
Bye.
Okay,
Thank you,
bye-bye.
bye-bye.
Thank you very much. Nice day. Bye.